Hello. It's 7 a.m. and I hope you're ready to do some calculus. This is a worksheet that we're going to work on this morning called Euler's Solution to Differential Equations. And it's got a number of problems designed to help you understand some of the nuances of this technique. And I'll try to be brief, but this could go on for 20, 30 minutes and we'll see. Anyway, first problem. Suppose a function f has a derivative y prime equals 4x minus 2y. It's got an initial condition, f of negative 2 equals 1. Our job, using a step of delta x equals 0.5, is to compute the Euler approximation for f of 0. Okay, so they've given us an initial x and an initial y, and we're going to put those in our table, and we're going to use the Euler's equations, and we're going to recursively generate new xy points and turn around and put them back into the process and just repeat until we move from negative 2 to 0, because this is another x. This is the x we hope to land on. And really the goal of the problem is to make an approximation for the y that goes with this x. So let's get started. I like to organize this in a table. The table looks something like this. And remember, to get a new y, the Euler equation says take your old y and add what is essentially an approximation for delta y. It's called differential. It looks like y prime times delta x. So in this problem, y prime is 4x minus 2y. That's going to go there. And delta x has been specified. They calculated it for us, and they want this to be 0.5. So in this table, we start with the initial x and the initial y. These two form a pair, and they specify a point that's actually on the curve. All the points that we generate subsequently probably are not on the curve, but they're probably close. So this says take the old y, add a calculation for the derivative right here, and these are both computed using these old values. So you have 4 times negative 2 minus 2 times 1, and then multiply by the step. And I designed this problem so all these values would come out, relatively easy to compute in your head. Here we have negative 8 minus 2 is negative 10, half of negative 10 is negative 5, plus 1 is negative 4. That is a new y value. It goes with a new x value. Now the new x's are really easy to compute, and I generally do all of those just sort of rapid fire. You're going to take this old x and you're going to add 0.5 to it. What's negative 2 plus 0.5? That's negative 1.5. The y that goes with that is negative 4. That's what we spent all this effort generating over here. Now, are we close to where we need to be? No, we're trying to get all the way to x equals 0. So if I keep adding 0.5, the next x here is negative 1. Add 0.5, the next x is negative 0.5, and add 0.5 to that, and you finally get to 0. So as you can see, we're going to have 1, 2, 3, probably 4 steps to get to where we need to go. Let's go ahead and generate a new y that'll go with this new x. Turn our lights back on here. So we're going to start with this old y. I know I said it was a new y, but as soon as it's computed, it goes out of style and you call it old again. So this is the sort of the recursive element of this calculation. Old y plus 4 times the old x minus 2 times the old y multiplied by the step 0.5. Okay, let's see if we can do this one in our heads. This makes negative 6 right here, negative 6, and this makes positive 8. Negative 6 plus positive 8 is positive 2. Half of 2 is 1, and 1 added to negative 4 is negative 3. That's your new y. So you get a new point where x is -1 and y is -3. It's probably not actually on the curve, but it's probably pretty close. Now we have 2 more steps to go, so let's not spend our whole afternoon talking about this. Oh, did I say afternoon? I meant 7 in the morning. Okay. We're going to take this old y. We're going to add to it a calculation for the derivative, which looks like this. 4 times the old x minus 2 times the old y. Complete all that calculation before you multiply by the step. What would that be? Well, there's -4 and there's +6, so -4 plus 6 is 2. Half of 2 is 1, and 1 added to -3 is -2. Seems to be a pattern going on here. Okay. -2 is the new y. As soon as we call it new, we put it over here in the old y category, and we just keep this process going until we're done. Old y plus the derivative, 4 times the old x, minus 2 times the old y, times the step. 4 times -0.5, that's -2. This is +4. -2 plus 4 is 2, and half of 2 is 1, and 1 added to -2 is -1. Bring that back over here, and I think we're done. Actually, we're not quite done, because what we want to do is make a little report. Euler's solution to differential equation is an approximation technique. And so what you don't want to do is just go to circle this and say, that's my answer. And you don't want to just write it down over here somewhere and put it in a box and say, that's my answer. And you definitely don't want to write f of 0 equals -1, because they're probably not equal. Instead, what you want to do here is use an approximation symbol. And then call attention to it so that some crusty old guy grading your paper can find it quickly and give you the points that you so deeply deserve. That's how you do problem 1. I'm going to scroll to problem 2, do a little erasing. We'll keep this going. Quick word, if you don't know who I am, my name is Eric. I'm a math teacher out in the state of Washington. This is March 2020, and probably like most of the schools around the country, we are shut down. And so I'm doing this for the benefit of my students. However, if you're a calculus student of any kind and you're studying Euler's solutions to differential equations, and if you can learn something from this, that's great too. All right, let's take a look at this one. This one's got a derivative of 10x over y minus 1. It's got an initial condition of a beginning x paired with an initial y. We'll use those to sort of prime the pump and get this table going. This problem does not tell us how the step delta x should look. But it does say that eventually you want to get to this x. That's like the final x that you want to get to. So remember, that's an x. How does one get from 3 to 2.6? The answer is you got to go backwards. How far is it from 3 to 2.6? -0.4. And I say negative because we're moving to the left. And we're supposed to do this in 2 steps. So if you're going to go from 3 to 2.6, you're going backwards, and that's a span of -0.4. If you're going to do that in 2 steps, each step has to be -0.2. So although they don't specify, it's not difficult to calculate the delta x for this problem. Delta x equals -0.2. Good news, 2 equal steps goes pretty fast, so this problem shouldn't be nearly time consuming as the last one. So I've got an old x, I've got an old y, I've got an Euler solution for a new y, it's always the old y plus y prime times the step. And keep your eye on this because that's what I'm going to continually use to calculate y prime. Also keep in mind that we figured out that our step in every case needs to be negative 0.2. Okay? So we'll fill up this table with the 3 and the 7 to get it started. Often called an initial condition. We'll do this calculation to make a new y number. And actually, before I do that, I think I'm going to go ahead and make all my x's right now. We're going to go from 3, and we're going to add negative 0.2 to that, which is going to get you 2.8. And then we're going to add negative 0.2 to that, and we'll be at 2.6 before we know it. So that's the easy thing to do, and I always do that first. It's like ice cream before mashed potatoes, okay? Now, for the y's, start with the old y, 7. Write down a calculation for y prime. That's this. So that's 10 times the old x divided by y minus 1, multiplied by the step, which is negative 0.2. 10 times 3 is 30, 7 minus 1 is 6, 30 divided by 6 is 5. 5 times negative 0.2 turns out to be negative 1. Negative 1 plus 7 is 6. Now, if you don't like doing mental arithmetic, you can do that on a calculator. Keep in mind, though, that there is sort of an expectation on a pretty famous national calculus exam, which I won't mention here. They would expect you to be able to do that without a calculator. Okay? So, there is a new y, but I'm immediately going to call it an old y and put it at the table. And I'm going to take these 2 points and run through the whole process again. So to get a new y, we start with an old y, 6. In this case, the derivative has this calculation, so that's 10 times 2.8 divided by y minus 1, so that's 6 minus 1, multiplied by the step. This is 28, and this is 5. 28 divided by 5 is the same as 56 divided by 10, so you get 5.6. So you have 5.6 times negative 0.2, and I believe that makes negative 1.12. So all of this is negative 1.12, and then you have to add 6 to that, and you get 4.88. Bring that down, and other than a report using an approximation symbol, we're done. So what does the report look like? G of 2.6 is approximately equal to 4.88. Okay, the next problem, problem 3, has got an Euler approximation in it. And I'll scroll this up and we'll get going on it. But it's got a lot of other fun stuff to do too. They're not necessarily related to the Euler calculation at all. Part A. Using 2 steps, compute an Euler approximation for 2.8. How much bigger is 2.8 than 2? 0.8. If you're going to get from 2 to 2.8 in 2 steps, each step is going to have a size of 0.4. See, that's 2.8 minus 2, that's 0.8. So that's how far you have to go, and you're going to do it in 2 steps. Each step is going to be 0.4. So for this problem, delta x equals 0.4. And you've seen this twice now, so let's just get on with it. Here's my table. Here's my Euler solution for a new y. It's the previous y plus the y prime calculation, which looks like that, multiplied by the step. and the step is 0.4 for this problem. You start this table off with 2 and 1. We'll go ahead and compute all of our x's right now. All we have to do is add 0.4, add the step. 2 plus 0.4 is 2.4. 2.4 plus 0.4 is 2.8. That gets us to where we want to be. The new y is the old y plus the derivative, which is x minus y squared, times the step. I hope you can read that. That's supposed to be an exponent of 2. 1 squared is 1. 2 minus 1 is 1. 1 times 0.4 is 0.4. 1 plus 0.4 is 1.4. So that one wasn't very difficult. This next one gets a little bit crazy, but we're tough. We can do this. We start with old y. We write down a calculation for the derivative, which looks like that. So that's 2.4 minus 1.4 squared. And then we multiply by the step. 1.4 squared is 1.96. 2.4 minus 1.96 gives you a 4. Looks like you have to borrow, so you're going to have 13, and you're going to get a 5, and then you won't have anything left here. So I believe you get 0.50, yes, you get 0.54 for that, and then you're going to multiply that times 0.4. And that's going to make 216 with 1, 2, 3 decimal places. And then you're going to have to add that back to 1.4. So 1.4 plus 216 gives you, this doesn't feel right, but I'm getting 1.616. Just in case I made a mistake in there, I'll try it with the calculator. And if the calculator disagrees with me, we will defer to the calculator. Yeah, it says 1.576. So, all right, we'll go with that. This comes out to 1.576, and that is a new y that goes with 2.8. And we're going to go ahead and say that's the goal. The goal is to figure out an approximation for h of 2.8. h of 2.8 is approximately 1.576. Now, I'm going to put that off to the side just in case I want to come back and refer to it in a minute. And then I'll go to some of the subsequent parts of this problem. The approximation is 1.576. Okay? If you're racing quickly, you can always pause the video, rewind it, whatever you need to do, and get the information. An equation for the second derivative. Well, the first derivative, which is going to disappear in a minute because I'm going to scroll this some more, was x minus y squared. This notation is read d squared y dx squared, and it quite literally means the derivative of the derivative, or y double prime. To compute this, we're going to go y double prime is the derivative with respect to x of what was the derivative formula in the first place. Okay, this is not too tough. I think we know the derivative for x is 1. The derivative for y squared, I would normally just say, hey, that's 2y. But when these variables don't match, you have to assume that y is some function of x, and that you really here only have the first factor of the chain rule. So you're going to have to multiply by the derivative of the interior of this squared function. The interior function is y, and its derivative is just y prime. In my class, if I'm grading your paper and you come up with that, I'm quite happy. But I think there might be an expectation in some cases for you to go ahead and plug this back in for y prime. So that would look like this. So you take the y prime out and substitute it for the thing that it's equal to. Okay? So now I have a point on a curve. I have a formula for a derivative. I have a formula for a second derivative. And I have a feeling we're going to refer back to that in a minute, so I'll erase this and I'll scroll. And in part C, it looks like we're supposed to compute an approximation for y double prime of 2. At the point P. So you have to remember P is 2, 1. And to make a quick sketch of what's going on here, you've got a graph called H. There's a point on that graph, 2, 1, about there. And if you calculate the value of the derivative at that point, which I don't think I've done yet, so what's y prime at point P? It's this calculation. So it's 2 minus 1 squared, which is equal to 1. That tells you that there's a tangent line going through here that's got a slope of 1. We just computed a formula for the second derivative. Part C, they want you to get a value for the second derivative at x equals 2. It does not tell you, however, that you're going to need to know the y that goes with it. Because as you can see, the y double prime has got x's and y's in the calculation. So that looks like this. Y double prime at point P is 1 minus 2 times y, that's a 1. And then times x minus y squared, so that's 2 minus 1 squared. What does all that make? This is 1, and this is 2. And they all multiply to make 2. 1 minus 2 is negative 1. So you probably heard in calculus that if a second derivative comes out negative, you have a curve that's concave down. So the curve could look something like this, or close to it. Try this pen. Now, why is it important to know all that? Because the Euler approximation has something to do with computing points on tangent lines. At least the very first step of it is exactly a tangent line. So if we went on out to 2.8 and got an Euler approximation like that, it's probably a little bit of an overestimation compared to what's on the curve here. Okay, part D, find the equation of the line that's tangent to the curve at point P. Well, remember how we do that. We use a point-slope form of a linear equation, and we just fill in the 3 blanks. Point P is the point 2, 1. So you know what x and y are, and you don't really need to justify those. You just put the 2 where it's supposed to go in the point-slope formula, and you put the 1 where it's supposed to go, and then just remember that this is where the slope is supposed to be. And you really ought to justify that somewhere on your paper. Slope in calculus almost always is computed by using the first derivative. And we had a formula for that, and we did that calculation back here. So somewhere on your paper you need to justify this number with a little setup like this. Now, as far as approximation for h of 1.7, they're telling you that at x equals 1.7, they want to know an approximation for the y value by going just behind this 2 and going on the curve up to a point on that tangent line. And we're going to get a number that's probably higher than what the graph of h would actually give us, because the tangent line is higher than the graph of h. H is the green curve that you see here. Okay, the process is actually easy. Take 1.7, plug it in there. (1.7 minus 2 is negative 0.3 times 1 is negative 0.3. Now add 1 to both sides, and you get y equals 1 plus negative 0.3, which makes 0.7. So again, here's x equals 2. You back up a little bit to 1.7 and you go up not to the green curve but to the black tangent line, and that's the y value that you're sitting at. Okay, finally, part E. Is the tangent line described back in part D above or below the graph of h near point P? You've heard me talk about that enough by now that you can probably make this determination. The answer is the tangent line is above. The justification is that we know we have a concave down graph. And we know that because the second derivative is negative. So I would write something like this. At x equals 2, which is the x value of point P, y double prime had a negative value. Okay, it's not important that it came out to, now I don't remember, I think it was negative 1. It's not important that it came out to negative 1, it's important that it came out less than 0. And that means the graph of h is concave down. So the tangent line, or more specifically the line tangent to the graph of h at the point P is above the graph of h. And I think that's the final item for this component. And then there are some technology problems that we do, and I've got those in a separate video. Thanks for watching. Hope you enjoyed. I hope you learned a lot. And I hope all of my students are feeling positive about the thing that we're going through in the United States and around the world right now.